Good morning, everyone. Today we're talking about mole ratios. How can the coefficients in a chemical equation be interpreted? Well, a balanced chemical equation can tell us the number of reactants and product particles, ions, atoms, molecules, or formula units that are necessary to conserve mass during a chemical reaction. Typically, when we balance the chemical equation, we think in terms of individual particles. However, in real life, the reaction represented by an equation occurs an unimaginable number of times. Short of writing very large numbers in front of each chemical in the equation, how can we interpret chemical equations so that they more realistically represent what's happening in real life? In this activity, we'll explore the different ways a chemical reaction can be interpreted. Model 1, a chemical reaction. Here we have nitrogen, a gas, plus 3 hydrogen, a gas, gives us 2 ammonia, also a gas. Consider the reaction in Model 1. What are the coefficients for each of the following substances? Well, there's nothing written here, right? There's nothing written here, so this is a 1, right? For hydrogen, we have a 3, and for ammonia, we have 2, right? Draw a particle model to represent that reaction. So if I have a nitrogen molecule that has 2 nitrogens in it, it reacts with 3 hydrogen molecules right, to form 2 NH3s. Here's one NH3. There's another one. Like that. Okay, so 1 nitrogen plus 3 hydrogens produces 2 ammonias. There's 1, there's 2. Okay. Consider each situation below as it relates to the reaction in Model 1. Calculate the amount of reactants consumed and products made. Okay, and then record the ratio N2 to H2 to NH3 and reduce the ratio to the lowest whole number possible. Okay, so for a single reaction, how many molecules of each substance would be consumed or produced? Right? For a single reaction, based on my numbers here, I'm going to have 1 of those. I'm going to have 3 hydrogens, and I'm going to produce 2. So my ratio here is 1 to 3 to 2. Okay? If the reaction occurred 100 times, how many molecules would be consumed or produced? Well, in this case, I would have 100 of those, and that would require 300 of those, and that would also then produce 200 ammonia. And that's going to be 100 to 300 to 200, but when that's reduced, right, if we reduce that, that's 1 to 3 to 2, just like the first one, right? And if it occurs 538 times, how many molecules would be consumed or produced? Well, I'd have 538 here, and then I'll need my calculator here, right? 3 times 538 is 1,614, and 2 times 538 is 1,076, right? So 538 to 1614 to 1076, and when that's reduced, it's 1 to 3 to 2, the same ratio. How do the reduced ratios in the last column compare to the coefficients in the reaction shown in Model 1? Well, if we look at those, right, my coefficients are 1 to 3 to 2, and all of my reduced ratios are 1 to 3 to 2. So here, they are the same. Use mathematical concepts to explain how your answer in part A is possible. Okay, well, if I have a reaction that requires one nitrogen molecule and 3 hydrogen molecules to produce 2 ammonia molecules, the mathematical concept that I'm looking for is the ratio, right? How many for each, right, is the same for all situations. Okay? So, even 538 is a small number of molecules to use in a reaction. Typically, chemists use much larger numbers of molecules. Recall that 1 mole is 6.02 times 10 to the 23rd particles, which is an enormous number of particles, right? Consider each situation below as it relates to the reaction in Model 1. Here's again our equation. 1 nitrogen, 3 hydrogen yields 2 ammonia. Calculate the number of reactants consumed and products made, and look at the ratio. Right? If the reaction occurs this many times, which is 1 mole, right? It occurs this many times, how many molecules would be produced or consumed? Right? Well, this would be 6.02 times 10 to the 23rd, right? 6.02 times 10 to the 23rd, right? Times 3 for my second answer. 1.806 times 10 to the 24th, right? And 6.02 times 10 to the 23rd times 2. For this one, 1204 times 10 to the 24th. And my ratio, right? Notice I have 1 of them, and I have 3 of them, and I have 2 of them, reduces to 1 to 3 to 2, right? How many moles of each substance would be consumed or produced? 1 mole, 3 moles, 2 moles produced, and again I get a ratio of 1 to 3 to 2. Right? How do the reduced ratios in the last column compare to the coefficients in the reaction in Model 1? They are the same. And that's really the point of all this, is we can use our equation to tell us how many we're going to get and use that as a ratio as part of our calculations. Right? Explain how it's the same. It's the same that we had up here. The ratio reduces to the same thing each time. Right? The ratio obtained from the coefficients in a balanced chemical equation is called the mole ratio. This is what this whole paper is about. It's a mole ratio. What's the mole ratio for the reaction Model 1? 1 mole of nitrogen to 3 moles of hydrogen to 2 moles of ammonia, NH3. Right? Why is it called a mole ratio? It's about the number of moles represented in the reaction. All right, the number of moles that's represented in the reaction. Okay, so use the mole ratio from the balanced equation in number 1 to solve the following problems. Right, you're going to set up proportions in the same way. We're going to use dimensional analysis the same way we did in calculating moles from grams and so on. So how many moles of nitrogen would be needed to make 10 moles of ammonia? Well, I start with what I'm given, right? I'm given this and I'm asked about this, right? 10 moles of ammonia, NH3, times, what's my ratio? I need my ratio. I have ammonia to nitrogen. In this case, my nitrogen is 1 and my ammonia is 2. Right, so I'm going to make that as a ratio. The nitrogen is going to go on top because I want the ammonia to cancel down here. From this equation, there's 2 moles of NH3 for every 1 mole of N2. Right, so I plug that in my calculator and I get 5 moles of N2. Right? How many moles of ammonia can be made by completely reacting 9 moles of hydrogen? Well, if I start with 9 moles of hydrogen, right, that's what I'm given, 9 moles of hydrogen. I'm looking for, here's my question, how many moles of ammonia? So I want ammonia, right, include the 3 there, my ammonia, right, to hydrogen. Okay, so in this case, there are 2 moles of NH3 for every 3 moles of hydrogen, right? So my moles of hydrogen cancel out, right? 9 times 2 divided by 3, right? 9 times 2 divided by 3, right, is 6 moles of ammonia. Okay? How many moles of hydrogen would be needed to react completely with 7.41 moles of nitrogen? Okay, so now we have more complicated math, but you just use a calculator then. 7.41 moles of N2, that's what I'm given. My question is, how many moles of hydrogen? All right, so if I look at hydrogen, hydrogen is 3 moles to 1 mole of nitrogen, right? So in this case, there's 3 moles of hydrogen, right? How many moles of hydrogen? For this many moles of nitrogen, nitrogen has a coefficient of 1, so 1 mole of N2, right? So 7.41 times 3 divided by 1, right? 22.23 moles of hydrogen. Okay? Consider this situation as it relates to this reaction. Calculate the number of reactants, calculate the ratio. All right, how many grams of each substance would be consumed or produced in the situation in question 4? All right, so you have to go back to question 4. All right? How many grams of each would be consumed? All right? For nitrogen, this is 1 mole, so I use my periodic table here. All right, I have 1 mole of nitrogen. Okay, nitrogen is 14.01, so 14.01 times 2. All right, this will be, we're looking for grams here, 28.02 grams. Right, hydrogen. We use 3 moles, right? We use 3 moles of hydrogen here. Hydrogen is 1.008 times 2, right? I have 3 of those, right? So my mass here is 6.048 grams consumed, right? And then how much NH3 is produced, right? It says here I use 2 moles. NH3, 2 moles is produced, right? So I add up those same numbers, 14.01 for the nitrogen plus 1.008 times 3 for the ammonia, right? That's my ammonia, times 2 because I have 2 moles of ammonia, right? 2 moles here, and that's 34.068 grams. Okay? So, 28 to 6 to 34. Can I reduce that at all? Divide it by 2, right? So I have 14 to 3 2, what is 34 divided by 2? All right, 17. All right? Can the mole ratio from a balanced chemical equation be interpreted as ratios of masses? There's a big resounding no there. All right? Use mathematical concepts to explain how your answer in part A is possible. This is an ugly ratio that doesn't match the chemical equation. All right, you probably can't see that. This is an ugly ratio that doesn't match the chemical equation, right? It can't be reduced that way, okay? As a group, you would normally be in groups working on this, but you're not, so it's just me. Develop a plan to solve the following problems. Remember that the mole ratio cannot be used directly in this situation. Note, you do not need the actual calculation here, right? What mass of nitrogen is needed to produce 30 grams of ammonia? What plan would I use? 1, convert to moles. 2, multiply by the mole ratio. And 3, convert back to mass. That's where we're going to be going in this whole video. All right. Now, I'm going to stop here. We're not going to do model 2 of part of this because I'm going to give you some problems to do, and we will come back to this part in a little bit. Okay? So, have a good day. We will talk to you soon.